perfect. So hello, everybody. My name is Mark, and I'm going to present joint work with Dominik on mechanizing second-order logic in Koch. I should maybe start off by explaining what second-order logic is. It's essentially an extension of first-order logic, where we not only quantify over individuals on a domain, but also over their properties or predicates on them. And this kind of second-order quantification is very common in everyday mathematics. For example, when we write down the induction principle for natural numbers, we usually quantify over all properties P at the frontier. In first-order logic, you would need to fall back to an axiom scheme and approximate properties via first-order formulas instead. Now, the relationship between those two formalizations of induction, and more generally the relationship between first and second-order logic, heavily depends on how we interpret those second-order quantifiers. And there are essentially two main semantics one can choose from here. First, there is full semantics, where the quantifiers span the full relation space. In our example here, this means that P really ranges over all properties on numbers. And in this case, the second-order induction axiom is indeed stronger than the first-order scheme, which is evidenced by the fact that it only permits a single model of second-order Peano arithmetic, which relies on this second-order characterization of induction. And as a consequence, you can show that many of the characteristic properties of first-order logic, especially completeness, no longer hold in second-order logic when working with full semantics. Alternatively, you can switch to Henkin semantics, where the relation space is generalized. And then you can see that completeness and many other meta properties that we know from first-order logic can be recovered. Of course, those results are not new. A good reference, for example, is the paper by Shapiro. Our contribution is that we analyzed them in constructive type theory and mechanized them using the Koch proof assistant. Before going into more detail on the results we've mechanized, I want to start off with some general remarks on our mechanization. To give a bit of context, because of previous work, we already have experience with mechanizing the meta theory of first-order logic, which at least syntactically is fairly similar to second-order logic. So we work with a syntax defined over a signature of function and predicate symbols, and then the terms are just these terms of first-order logic consisting of variables and function application, and the formulas are extended by predicate variable application and n-ary function, n-ary predicate quantifiers, so n-ary second-order quantifiers. Because of this similarity to first-order logic, we could reuse or adapt many of the design decisions we used in previous first-order developments. For instance, we make use of the brown encoding of binders. Equality is not built into the syntax. Instead, we decided to, when needing equality, we just add it as a predicate symbol and axiommatize it. And then on the Koch level, there are many nice features that help us during the mechanization. For instance, we make use of Koch's type class mechanism to encode the signature so that it can be derived automatically from context, which is quite handy. And besides first-order logic, people have also worked on mechanizing higher-order logic. But as far as we're aware, we're the first ones to mechanize the meta theory of second-order logic. And while having this previous experience on first-order logic is definitely helpful, mechanizing second-order logic is definitely harder than mechanizing second-order logic. And there are also unique challenges to second-order logic that don't show up in higher-order logic. For instance, since we want to support quantification over predicates with arbitrary arity, this means that things like the Brown scoping or the definition of substitution and environments can get more difficult. Also, we want to focus on quantification over predicates here, but we also investigated how one would best implement or formalize quantification over functions. And in our meta theory of constructive type theory, this can actually get a bit tricky. Okay, so let's start off with full semantics, which is essentially just an extension of the usual task semantics we have in first-order logic. So models consist of a domain and an interpretation for function and predicate symbols. And then the semantics just maps the connectives and quantifiers to their counterpart in our meta theory. And as I said, in full semantics, the second-order quantifiers range over the full n-ary relation space. I also briefly mentioned second-order Peano arithmetic, which besides induction also relies on the other axioms shown here. And as mentioned, if we work with full semantics, then there's only a single model of second-order Peano arithmetic. This property is called categoricity. So P2 is categorical, which means that all of its models are equal up to isomorphism. And this can be seen fairly easily. So if we have two models of P2, we can define a relation by relating the zero interpretations and relating the successors if x and y are related. And then you can show that this is indeed an isomorphism using the induction axiom. This is essentially just follows the normal textbook proof, but one interesting point to make here is that we need to give this isomorphism as a relation, and it's not possible to give this as a function. And the reason for this is that our only means of inspecting the structure of individuals is via the induction axiom, which is inherently propositional. So we cannot extract computation information from it, and therefore we need to stick to relations here. But nonetheless, categoricity is, of course, a major point of disagreement between first and second order logic, because in first order logic, it's simply not possible to give a categorical explanation of the natural numbers because of the wenheim-Skolem theorem. But this in turn, of course, also means that second order logic does not satisfy the wenheim-Skolem property when working with full semantics. We can also use this categoricity result to show that second order logic is not compact. And for this, we can look at the infinite theory that consists of taking P2 and then adding statements that basically assert that X is not a numeral. And if we only look at a finite subset of this theory, then we of course have a model. Just take natural numbers and choose a value for X that is not excluded. But the natural numbers are not the model of the whole theory, because then there is no number we could assign to X. And as a consequence, since the natural numbers are also the only model of P2, we can conclude that this theory does not have a model and thus contradicts compactness. Interestingly, a very similar argument can also be used to show that second order logic is not strongly complete when working with full semantics. And to clarify the terms here a bit, when speaking about deduction systems, we think of predicates that work on a list of formulas as context. So normally, completeness is phrased in terms of those finite lists. However, you can also lift this deduction system to theories, that's potentially infinite theories, by saying that a formula holds under a theory or is provable under a theory if there's a finite subset of the theory that suffices to prove the formula. And this gives rise to the stronger notion of completeness in terms of theories. And essentially using the same compactness argument from previous slide, we can show that second order logic is not complete in this strong sense. And surprisingly, this does not even require computability assumptions on the deduction system. But of course, this only rules out completeness in the strong sense and not the weaker notion where you only have finite contexts. In order to get this, you need a more involved proof and also the assumption that the deduction system is enumerable. Usually, this is given as a consequence of Gödel's first incompleteness theorem, which in terms of mechanization is of course fairly heavy. Luckily, there's an alternative. It's fairly well known that you can also phrase this in terms of computability theory, which, depending on how you do it, can be way easier to mechanize than a concrete Gödel sentence. We also make use of the synthetic approach to computability theory, which relies on the fact that functions definable in constructive type theory are always computable. So instead of working in a concrete model of computation, we can actually synthesize the notions of computability theory inside of a type theory. For instance, we can say that a problem is undecidable if an undecidable problem reduces to it, and this reduction is then given by a normal Koch function. Similarly, a problem is not enumerable if a not enumerable problem reduces to it. Now, in order to get incompleteness, we first show that validity in PA2 is not enumerable. And we do this via a reduction from the complement of Hilbert's 10th problem, which is not enumerable, and this is also already mechanized in Koch. H10 is about deciding whether the Diophantine equations, so equations between polynomials with natural coefficients, have solutions in the natural numbers. And we can take such an equation and just encode it as a formula in second order PA, and then bind the variables with an exponential quantifier. And then you can see that the equation has a solution if and only if this formula holds in natural numbers. Or since we want to reduce from a complement, the equation is unsolvable if and only if the negated formula holds in natural numbers. And then since the natural numbers are the only model of PA2, this is the same as saying that the negated formula holds in PA2, which finishes the reduction. So now that we know that validity in PA2 is not enumerable, this immediately yields incompleteness, because if we had a complete deduction system, then this system would enumerate all valid formulas. So we get incompleteness, or more formally, that the existence of a sound, enumerable, and complete deduction system would imply that the complement of H10 is enumerable. We can also use this same H10 reduction to get undecidability results for second order logic, namely that validity and satisfiability is undecidable, especially in the empty signature. And the trick here is that you can embed the signature of PA2 inside of a second order formula by quantifying over it. And the same for satisfiability, respectively. Okay, let me now switch over to Henkin semantics. The basic idea here is that instead of quantifying or instead of ranging over the full relation space, the second order quantifier should only range over the relations that are contained in a special universe. And this universe is then specified by a so-called Henkin model. We want to constrain this a bit and say that the universes should satisfy comprehension meaning that they should contain at least all second-order definable properties. When speaking about completeness, we of course also need a deduction system. For this, we just take the usual first-order ND system and extend it with rules for second-order quantifiers, and also this comprehension axiom scheme, which corresponds to the comprehension requirement of universes and just gives us access to properties P that behave like formulas. And the result by Henkin is that this system is indeed complete when working with Henkin semantics. And the proof is just the normal Henkin-style completeness proof that we would also use in the first-order case. However, there's also a different, and in our opinion, more interesting way you can get completeness for Henkin semantics. And this is related to the fact that second-order logic with Henkin semantics is essentially just many-sorted first-order logic. To see this, we can argue that a second-order formula phi can be translated to a many-sorted first-order formula phi star by adding a sort for individuals and then sorts for predicates of different arities. And then we can just replace predicate application with a custom application symbol that represents this. Then you can show that we can transport the completeness theorem from first-order logic to second-order logic without needing to prove it from scratch. However, we don't want to focus on the many-sorted case here. We want to focus on monosorted first-order logic instead, because it's the more common formalism, and we already have a mechanized completeness proof for monosorted first-order logic. The usual way you would go from many-sorted to monosorted is to add some kind of predicates that guard the quantifiers, so that to make sure that the objects we're talking about actually correspond to the right sort. That's, for example, the approach taken in Van Dalen's textbook. But if you want to use this translation to actually get completeness, you would need to show that first-order probability of the translated formula implies probability of the initial formula in the second-order system. And this turns out to be very difficult. Van Dalen gives some vague hints, but at least we were not able to come up with a proof here. But we're also not the only ones who looked at this. There's a 2003 paper by Nuendorf Ali, who also investigated this, and they also were not able to come up with a proof. Instead, they propose a slightly different reduction or translation function, where the basic idea is that X and P represent individuals and predicates at the same time. And then depending on where they occur in the arguments of the application symbol, they are either interpreted as a predicate on the first place or as individuals in every other place. We have mechanized this translation, which then allowed us to transport completeness from first-order logic to second-order logic. Concretely, this required verifying the following results. First of all, we want to show that Henkin validity of a formula corresponds to first-order validity of the translated formula in the translated theory, where we need to add this extra bit of information that makes sure that we only consider first-order models that satisfy comprehension. Then, by first-order completeness, we get a proof in the first-order system, which we then need to turn back into a proof in the second-order system of our initial formula. And this last part is by far the most challenging, because you cannot simply do an induction on this first-order derivation, because the formulas have this specific shape. Instead, Nuendorf Ali defined a backwards translation function that turns second-order formulas back into first-order formulas back into second-order formulas, which satisfies the following two properties, which then allows you to construct this direction. Putting everything together, this gives us the following result, that if first-order logic is complete, then second-order logic with Henkin semantics is also complete. This is the result we have in the paper. In the meantime, we've actually merged the existing first-order completeness development into our mechanization. So we now have the fully mechanized completeness result under extruded middle. And similarly, you can also get compactness under extruded middle. Overall, this part was by far the hardest of this project for multiple reasons. First of all, while writing down those translation functions on paper is very straightforward, actually doing it, implementing it in the Brown setting is not that easy, because you need to be very careful to get the scoping right. And also verifying those properties here below is challenging, because you need to work in this deduction system, which can get quite tedious over time. So we think that it would have probably been easier and less work to obtain completeness via the normal Henkin-style proof. But we think that this approach is actually more interesting, because it gives you this deeper insight that Henkin semantics make second-order logic collapse to monosorted first-order logic. And also, this result not only gives us completeness, but we can use this translation idea to also transport many other properties of first-order logic. To demonstrate this, we have shown that you can also translate wenheim-Skolem. So we can take the wenheim-Skolem property from first-order logic and then get the wenheim-Skolem property for second-order logic using this translation idea. So to wrap up, our mechanization is fully constructive, except for the completeness and compactness result shown before, and consists of overall 8,000 lines of code and 1,500 lines reused from the Koch library of undecidability proofs. Also, our undecidability results that are showed in the talk are contributed to this library. More details can be found on the project page here. In terms of future work, it would be interesting to actually mechanize the wenheim-Skolem theorem from first-order logic, because then we could instantiate our translation and then get wenheim-Skolem for second-order logic for free. And this is actually work in progress. Then it would also be interesting to look at other second-order externalizations, for example, second-order set theory, or look at concepts like internal categoricity, though this would be fairly difficult and might require additional tooling to help working inside of the deduction system. All right, that's all. Thank you very much for your attention.
Thank you, Mark, for the interesting talk.
Right.
We're ready to take questions. First, local questions. So Mark and Dominik are here. Yeah, please.
Any questions?
Any online questions? Sorry, Steve. Was there a question?
Andrew has a comment, but if there are other questions.
Yeah, please.
I should defer this comment until the actually important questions have been asked. So it was a very interesting talk with very many interesting historical citations going back to 1888, which I appreciate seeing sort of the history of this laid out until it finally gets mechanized, as you have done. So the trivia question is, what's the earliest paper you cited on a slide whose author is still alive? And I conjecture it's Davis and Putnam, 1959, which was published before anybody in this room was born. And Martin Davis is still alive at age 93. And of course, Davis Putnam is the foundation of SAT solvers.
Thank you for the comment. Mark and Dominik, please assess the accuracy of this comment.
We can replicate this.
To Andrew. So now we have a question from Benjamin Werner. Please, can we post this? Did you use some of the neat libraries for helping the treatment of De Bruijn indices?
We did not. So we did the round stuff by hand. Because we largely followed the existing first-order developments we have in the library, which also does it this way in order to be more compatible. That was the approach we chose.
Okay, so because some of them are developed in your group or by some of your co-authors, some of these neat tools.
Yes, there's autosubs, yeah.
So we in fact used autosubs before on, I think, all projects we did with first-order logic up to completeness. And then when we started working on these undecidability results, we wanted to switch to a setting because we want to incorporate as many other projects as possible. And autosubs, unfortunately, has this issue that it assumes function extensionality. And so we decided that we basically reconstruct, so it's based on exactly the same ideas as autosubs, so parallel substitutions, and then you prove enough substitution lemmas, so you have tactics that basically normalize substitution terms. And we did this by hand without using function extensionality. So we are not incompatible with someone adding a project to the library which would be in conflict with function extensionality. So, but in spirit, we completely follow the ideas of the autosubs tool.
Okay. So there's also a comment by Dan, which I think is worth reading, is interesting. So it seems like your formalization is hooked into many other formalizations of serious mathematical results. I think this is really cool, especially in the light of Andrew Apple's talk on ecosystems. So let me also ask a question. This is about your general synthetic approach to decidability, and basically you draw conclusions in terms of synthetic undecidability and decidability from your results. How does this compare with, let's say, the terrestrial way, the mundane way of modeling undecidability, whether there is an implication between the two notions? And I guess this goes back to the notion of hooking up existing results. So, for example, you mentioned that incompleteness is very difficult to formalize. You have the result by the formalization by O'Connor of Gödel's first incompleteness theorem in Koch. But I guess the key to use such results, maybe not in that exact form, would be to connect your synthetic undecidability with the more standard notion. So how does this go?
Yeah, so it's definitely easier to work in the synthetic approach because you don't have to model don't have to work in a concrete model of computation. You can of course assume the axiom of post theorem, which then connects the sides and then says that the meta theory actually behaves this way, that everything is computable, because otherwise, yeah, you are only working in the synthetic sense. Yeah, but this would be the connection, I think.
And
yeah, sorry, please, Dominik.
There's some tooling. So in principle, if you write down a function just on primitive first-order inductive types in Koch, then we have tooling that you can click a button and this gets extracted to a verified Turing machine or a verified term in lambda calculus. So by this, in principle, you can get the normal textbook results from all the work we do. But this only, unfortunately, it doesn't easily scale to first-order logic and second-order logic because there the framework we use, the syntax we represent is a bit too involved for these tools. So in principle, we are a click away. In reality, it's a bit more.
It's 2 clicks away in reality.
I would even say maybe a week of headache, but
I see.
in principle, every function you write down in Koch in the empty context, you can always write down a Turing machine if you want to dive down this way. So in principle, there is no limit to this method.
Okay, thank you. So are there any other local questions?
Yep, one in the back. Just a second.
No rush.
Hey, thanks for the interesting talk. I'm curious about your treatment of equality. You said that you just treat it as a relation. You don't build it into the system. But one of the things that means is that you don't have the substitution as something that you can talk about within your system. How difficult would that be to add, and what complexities would that add?
What exactly do you mean in terms of substitution?
So you really can't talk about, unless I'm missing something, you really can't talk about the fact that if something holds for some deep formula, I mean, you can do it for some property that's atomic, but for a deeper formula, you can't do substitution, right? You can't say, well, if this holds for E and E equals E prime, therefore holds of E prime. Or am I missing something?
So we have equality. It's just, it's essentially axiomatized. So the way you would do it in first-order logic, you can also just axiomatize it. Interestingly, so if we look at, for example, second-order PA, you can actually show that the interpretation of the equality symbol exactly corresponds to real equality because you have this strong reduction, and then you can actually verify this. Also, another approach would be to use the Leibniz characterization of equality. So instead of adding it to the syntax, or instead of adding a symbol for it, you can use Leibniz. We decided against this to be more compatible with the first-order fragment because we used some arguments that only work in first order and wanted to make this connection clearer. Therefore, we chose this way because it's the most compatible.
And in general, I think it's always the case if you axiomatize equality and just axiomatize that it is a congruence for all the symbols you have in your signature, you can always derive the Leibniz rule. So the substitution rule can be always seen as a possibly finitary axiomatized rule for equality, as long as your signature is just finite.
All right. So if there are no more questions, we can thank the authors again.